Right. Now it's supposed to be on. Did you get a message about it?
Yes, we're
Okay,
recording.
perfect. And maybe now we just start this short discussion of the midterm test, right?
Okay.
I think we just to have this information. Just to remind you, it's next week, so it is Monday, February the 28th, and it is instead of the lecture. So there will be no lecture next week. Instead, there will be the test. So it should be starting at what 10 to 3, and then it lasts for 2 hours, and then there are plus extra 15 minutes for you to upload, send, whatever, do whatever.
Technical margin.
Yeah, technical margin. But of course, well, I don't know, maybe you want to continue working for 14 minutes and then 1 minute is enough to send stuff, but okay, whatever it is. And those of you who want to participate in the midterm test, so please send your emails.
Yeah, that is absolutely compulsory.
Yeah, this is really necessary, because then I don't quite know, Ian, what will be the system. You will be emailing the problem set.
I'll email the problem set at exactly 1450 by synchronized emailing from Gmail, probably.
Okay, so basically that's, if you want to participate in the exercise, please do that. Because
if I don't have emails for anybody and they don't get it, then they hard luck. There's nothing to do. There's no way out. Right. Okay. I'll probably put a notice on the Telegram thing about it.
And then when you are finished with your problem set, you also need to submit, I guess, by email, right? Or
yeah, or I'll send the instructions for submission. If I find a better way, I'll put it, but it probably has to be email. It's not, I don't like it very much, but if I don't find a better way. Can I just make one comment? I didn't think of this before, but when usually people take a photograph of their work with a mobile telephone, that's the usual thing. And the result can be truly enormous files. I mean, I have received files of 5 pages of 20 megabytes, right? So it would be great if you just spend 20 minutes to check before you even do it today or tomorrow, to find out how to arrange that a photograph is not enormous. It's absolutely possible to get very good quality in 10 pages in half a megabyte easily, but because I have seen such things. So it would be great if you could do that, because otherwise you will maybe overflow my mailbox.
Okay. So maybe I have one more comment, but now on the contents of the test. So the test consists of several problems. Of course, they are not the same problems as you had in exercises, but certainly it's inspired by the course and inspired by exercises. Obviously, this is a take-home exam, so you do it on your own. So you're allowed to use all the lecture notes and all the solutions of the previous problems we had on the problem sets. And here we kind of we're not of the same mind. I think maybe our problem set is too long for 2 hours. And right, Ian, you think that
it's okay.
The problem set is just okay. But in any event, there is a possibility that the problem set is too long. So in this case, you shouldn't worry. You should just solve whatever you can solve. You shouldn't run to absolutely address all the questions. Address the questions that you have time to address, because, as I say, I wouldn't exclude, to me, let's say, if I were a student, to me, it would be a somewhat longish problem set for 2 hours. But Ian says for him, that would be just a perfect.
No, because they are clever students, Anton. I have high expectations of these
No,
people.
but I mean, you see, this is just to share with you our
to lighten the pressure. To lighten the pressure.
Okay. So yeah, no pressure whatsoever. Okay, perfect. So I don't know whether there are any questions about the midterm of next week. Okay, perfect. But I mean, you can also ask your questions later, or you can write to us emails, whatever way. So we would be very happy to answer. So now we still have some stuff to finish from the last class, so maybe let me start in the following way. So that's a follow-up of the last class, and we're looking at say S1 actions on vector spaces. So, and this is a linear S1 action. And so here is a proposition which is probably sort of obvious, but that's the first instance where we're using something that we'll be using quite often later on. So we introduce an auxiliary structure, and I claim that in such a situation there is always an S1 invariant Euclidean metric on our vector space, right? We study symplectic geometry and symplectic linear algebra. A priori, we don't need metrics, but sometimes we use them, and actually quite often we use them in the proofs. So let's first look at this situation in this baby case where we're just looking at a vector space. So let me recall that Euclidean metric, this is a positive definite symmetric bilinear form, right? So let's say G. Let's choose any Euclidean metric on our space V. And now we can use the following idea. So we average this metric under the S1 action. So U and V are vectors in V, and I define the new metric G bar as an average. So 1 over 2 pi integral over S1 G, and here I act by my S1 action on the vector U. I act by the S1 action on the vector V, and I integrate over the circle. So now claims. So G bar is again a Euclidean metric. Essentially, what you need to check that this is still positive definite. But since G is positive definite, if I evaluate it on the same vector, right? If I put U equal V, then everything under the integral will be still positive. So the integral is positive, right? So it's still a metric, and it is now S1 invariant. So if it is obvious for you, it's good. If it's not obvious, check it. So right. Now maybe one remark. Maybe one remark, or maybe just first, maybe something to say informally. Basically, you can play such a game with any compact group, and I will often be doing things by averaging for S1 because it's just easier. But you can do so it works. So this trick works for compact groups. So you can often average things, and you obtain invariant things with the same properties. So here we did it with a metric, but even today there will be another instance where we want to average. And actually, that's one of the main things when you work with compact groups. So this was one remark. Maybe another remark is as follows. So G bar is invariant, which means that now for any theta, the value of G bar on U and V is the same if you rotate U and V by theta, right? So that's the invariance. So that's the invariance property. So now let's take a derivative of this equation at theta equals 0. And we get the following. So we get G bar, and here D of U V plus G bar of U D of V is equal to 0, where D, perhaps I don't know whether you remember the notation from last time, that's the derivative of rho of theta at 0, or sometimes we say this is a generator of the S1 action, or this is the image of 1 in the Lie algebra of S1 under the representation rho. So this is actually also equal to whatever rho of 1 or rho of I, depending how you identify what's your picture for the Lie algebra of the circle. So so we have this property for this generator D, and now let's do the following. Right, G bar is a Euclidean metric, and we can choose an orthonormal basis. Sorry, frame, because I'm now doing some differential geometry. So choose an orthonormal basis for this Euclidean product G bar, right? Once you've chosen a basis, D will become a matrix. And this property that we have here, so this property will translate into the following feature of this matrix. So D transpose is equal to minus D. So this will be a skew-symmetric matrix in this basis, in any orthonormal basis of G bar. Okay, so far so good. Now let's throw in one more structure. Recall that we actually wanted to look at symplectic vector spaces with an S1 action, and the symplectic structure is supposed to be S1 invariant. So we have now S1 acting on V omega, which is now a symplectic vector space. And we assume that omega is S1 invariant. So omega satisfies a similar condition to G bar. So this is omega of UV. Right. Well, now, since we now have this auxiliary invariant metric, we can say that there is a unique operator, let's call it A omega, such that omega of UV will be G bar, and here A omega of U V. So these are things that you quite often do in the elementary linear algebra course, right? So we now have two bilinear forms. One of them is symmetric, it's G bar. Another one is skew-symmetric, it's omega, and we express one of them as the other one plus an operator. Usually in the linear algebra course, you would apply it to two symmetric bilinear forms and try to compare them. But okay, now one of our forms is skew symmetric, so be it. Okay, and now it's easy to figure out that the fact that omega is skew symmetric implies the following equation, which resembles something that we've already seen before. So G bar of A omega U V plus G bar of U A omega V is equal to 0. So that's so this equation, it's easy to check. It encodes the skew symmetry of omega. But you see, it resembles very much the equation in yellow at the top of the page that we had for D. So this means, again, in an orthonormal basis for G bar, our operator A omega is skew symmetric, right? So finally, one more observation. So we know that there is one thing that we haven't used yet. So we know that omega is S1 invariant. Right. And what does this condition say? So this condition says that G bar A omega rho of theta U rho of theta V is equal to G bar A omega of U V. So that's now in this a bit weird language, that's the S1 invariance of omega. Now we know what to do with such equations. We take d over d theta at theta equals 0. And what we get is the following equation. So we get G bar A omega of D of U V plus, sorry, get confused myself. G bar A omega of U D of V is 0. Now, it's a simple linear algebra exercise to show that, again, in this orthonormal basis, so this equation gives you that D and A omega are two commuting operators. Okay. So with this auxiliary construction, we end up with the operator D, which is skew symmetric on our basis, the operator A omega, which is skew symmetric on our basis, and they commute. But you probably know the standard theorem in linear algebra that if you have two self-adjoint operators which commute, then they have a basis of common eigenvalues, right? That's one of the things that we learn in linear algebra. Now these are skew symmetric operators. Let me tell you what we know from linear algebra about such pairs of commuting skew symmetric operators, and then you tell me whether you believe it. So, so I claim this implies the following. So you can actually bring them both at the same time to a normal form. For instance, for A omega we know it's non-degenerate because it corresponds to a symplectic form, and I put it into this sequence of 2 by 2 blocks. And for the blocks, I can probably choose the sign. Actually, I don't remember what sign I usually choose. Sorry about that. For instance, we can say this is 0, 1, -1, 0, right? Or we can change sign. So these are the standard blocks. And D will be then of the following form. So it will be in the same 2 by 2 blocks. So let me write something here, and then we discuss. So this will be 0, minus n1, n1, 0, 0, minus n2, n2, 0, and so on. But then maybe at some point it stops, and then n's, they might also be 0, right? D doesn't need to be non-degenerate. So in general, what will happen, perhaps some blocks in the end, they will have only zeros, or maybe not, depends. So that's a canonical form for a pair of 2 skew-symmetric operators which commute. And you can imagine the proof. You can complexify the situation. So then those skew-symmetric operators are anti-self-adjoint, right? So anti-self-adjoint, which this means you can diagonalize them at the same time. And then when you go back to the real picture, that's what you have. That's basically the situation. Maybe one more comment about those ni's. So ni, they're all integers, and that's because we have an S1 action, right? So the exponential. So the exponential of TD should be 2 pi periodic in T, because otherwise it wouldn't be an S1 action with a period 2 pi, and that's why those n's, they come out to be integers. Okay. So that's how it looks like. And if you recall, maybe you can look up in the notes of the previous lecture. That's basically what we wanted to prove. So we wanted to prove that if we have a symplectic structure on a vector space, which is S1 invariant, then we can find a simultaneous normal form, the Darboux form for omega, and that's what I'm doing. So this is Darboux. And at the same time, there will be a normal form for the S1 action. So it's kind of interesting that one would imagine that it might be more complicated, but it all reduces to 2-dimensional representation. So there is nothing else. And a similar story would also work for actions of Torre, because there you would have more of those operators D. They all commute with each other and with A omega, and you can still simultaneously bring them to a normal form. So the same. Works for actions of Torre. Right. Okay, so that was the discussion we haven't finished last time, and we're going to use it later on, and also we're going to build on this discussion in the future. But now I want to start a new topic, and in fact, it's not maybe very logical in the course, because I should have done more of the theory of G actions on manifolds, but I want to introduce the main actor of our course. So we'll talk later about more on G actions, but now we're going to discuss the definition and properties of Hamiltonian G spaces. So that's the definition that we've already seen in the first class. And now let's go over it in a bit more detail. So we start with a sequence of definitions. So the first definition, we say that the G action on M omega is symplectic. If, well, obviously, if the action preserves the symplectic structure, and here I use a somewhat non-standard notation. I'm saying that the group element G is mapping a point M to a point G times M on my manifold. So the two form is invariant under the G action. So I'm choosing a point M, and here is a point GM, and here is the transformation given by the element G of my group. So pulling back, the two form gives the same form. Now a small remark. If G is connected, and we basically always or almost always consider connected groups, so then the two things are equivalent. So then G acting on M omega being symplectic is the same as Lie derivatives with respect to fundamental vector fields of omega being 0 for all x in the Lie algebra. So these two things are the same, right? That's similar to the statement that we were discussing last time about representations, right? The fundamental vector fields, they give a representation of the Lie algebra, and so the property of the representation of the Lie algebra being trivial leads for a connected group to the property of representation of the group being trivial. So it doesn't act. So omega doesn't change. Right. So maybe again, for those of you for whom it's not obvious, I encourage you to check it, or at least try to convince yourself. And if not, come back to us with questions. Right. So maybe here the calculation that we already done once, I believe, but still, I think it's not a bad idea to repeat it. So suppose that this is true, right? So we have the Lie derivative of omega being 0. Now we can use the Cartan's magic formula, which says that this is the same as the sum of two terms. And one of those terms is 0 because omega is closed. So this is equal to d iota xm omega. And of course, this implies that the form iota xm omega is closed, right? So that's just another words to say it. So if we have a symplectic action, all those one forms, contractions with all fundamental vector fields, are closed. So for all x in G, and in fact, this is an equivalence. So that's the same. So the action is symplectic if and only if all of those one forms are closed. So that was the definition number one. And we continue immediately with the definition number two, which says the following. So again, we consider an action of G on a symplectic manifold, and we say that this action is Hamiltonian if there is a function, a map from M to the dual of the Lie algebra of G, which satisfies the following equation, which is probably the most important equation in the course, because everything else kind of follows from it. So now this contraction of omega, this fundamental vector fields, is minus the differential of the pairing between mu and x. So this is for all x in G. So note that so mu is a function with values in G star, so it's a vector valued function. But this pairing of mu and x, this is just a smooth function on M with real values. So basically what we're saying now is that the one forms iota, xm, omega, they are not only closed, they are actually exact, right? So this equation is called the moment map condition, and the function mu, or the map mu, which satisfies this condition, is called the moment map associated to the G action. In fact, so this is, at the moment, it's not very visible, but it's a huge advantage to have a function or a map instead of a G action, or like kind of, it's after all, it's easier for us to work with functions or with maps than to work with actions. Maybe that's one of the reasons why the moment map theory is so powerful and so rigid. So of course, in the course, we'll have many examples of Hamiltonian actions. We'll start with some simple ones today, and then we'll continue with many more. But today we're going to discuss also some general properties of moment maps, and we will continue also next time with some general properties. But I start with the following obvious remarks. So first observation, suppose that for some x, the cohomology class of this one form is non-vanishing. Then obviously there is no moment map, right? Because the moment map condition, it says that this form is exact. So if it's not exact, then no moment map, right? So this is an obstruction for existence of the moment map, and this is an abstraction for the action being Hamiltonian. Right? On the other hand, if H1 vanishes, then all the closed one forms are exact. And then the moment map clearly exists. So once you're given a symplectic action and H1 vanishes, then yeah, there is no doubt that there is a moment map. Right. Here, let me.
May I have a question?
Oh, yes, absolutely.
And is there any way to go kind of backwards? So suppose I know that the well, that iota of omega is well, I know that iota of omega is exact, but
Okay.
I don't know that the function looks like, well, looks like.
Okay. Let me, actually, it's a good question. You know, I wanted to cheat and not to say it, but you know, two things that I'm very happy about, that you don't let me cheat, and also I was a bit worried that there were no questions. So you're right, of course. Let me say the following. Suppose that I know that all those iota x omegas are exact. So let me choose a basis. EI in G. So we're doing like, you know, in some of the exercises, we're dealing with infinite dimensional spaces and infinite dimensional groups, but officially in the course, everything is always finite dimensional. We'll see, maybe it's not going to stay like that all the time, but in any event, so we just choose a linear basis in G, and we know that, right? We know that all those one forms, they are exact. So so there are some functions, let me call them HI, right, which satisfy this property. So now we can just put mu to be equal to sum over I, HI. So this is of M, and here I simply put the dual basis, right? So the dual basis of G star, and then it's a very easy check that this is indeed a moment map. Of course, I think you maybe let me interpret your question. You may be worried that who knows, maybe there are many of those moment maps, right? But I'm now showing you how to choose one. Of course, it depends on the choice of the basis, possibly, but at the moment we don't care.
No, I actually don't care about the choice of mu. For me, it seems that like they kind of all similar up to kind of S or N action on G.
We'll now discuss it, but actually you're not quite right, but we'll discuss it now in some more detail. But I now showed to you that I can always choose, if I know that those one forms are all exact, then I can define a moment map which would serve for all the vector fields. Is it right?
Yeah, that was, yeah, this is
that was the
perfect
worry,
answer
right? Maybe
on my question.
Yeah, maybe so I think you were worried that maybe they're exact, but maybe they're not of that form, but they're actually always of that form for some mu.
I have another question.
Sure.
So often in textbooks, mu is also required to be G equivariant.
Oh, we'll come to it. So we still have 40 minutes of the class. You're right. There will be, we're going to discuss it today. Okay.
I think I'll just put up the problems now, by the way. That reminds me.
Okay, sure. Yes. So at this point, I wanted to
go back for a second.
Sure. Yeah.
So
absolutely.
we just showed that if a manifold has zero first cohomology, then any symplectic action is automatically Hamiltonian.
That's right.
It's very surprising. Okay, thanks.
Wait, but I mean, let's say symplectic action of a connected group, right? But no, I think you see, maybe then, maybe you kind of one should have been surprised somewhere here on this page, right? So the action being symplectic is the same as the symplectic form being annihilated by Lie derivatives of fundamental vector fields, and in turn, this is equivalent to that. So after that, of course, if there is no H1, I mean, there is no abstraction for being Hamiltonian. Okay, let's look at the,
Still, what about G equivariance? If we require, this construction might not work.
yeah, let's we're going to talk about G equivariance just a little bit later today.
Okay.
So we'll discuss it even in some detail. Okay, so let me just give a couple of examples. We can say an example and a counterexample. So the example is M being R times S1, and it carries the standard symplectic structure, dpvh d theta, and I take as xm d over d theta. So S1 acts by rotating S1, right? So just S1 acts on itself by rotations, and then the generator of that action is just simply the vector field d over d theta. So I can now compute iota xm omega, and I'm getting minus dp. So the conclusion is mu of p theta is equal to p. So now, and this is, it takes values in R, which I interpret as Li of S1 star. So this is, of course, an elementary calculation, but this is an example of a moment map. So the action is symplectic, this action by rotations, and we just compute that moment map. By the way, maybe let me return just for a second to something that I had before, and or maybe let me write it here. So remark. So suppose we have a moment map condition. So then it actually implies that the action is symplectic. Because, you know, I just, in the example, I realized, I said, oh, the action is obviously symplectic. But I mean, a priori, we should check it. But in fact, not really. Because if you have a moment map condition, then again, right, you're using the Cartan magic. And the second term dies out because omega is closed. But then the first term gives you minus d square of mu x, and d square is 0, so it is 0. So in fact, once you have a moment map condition, you don't need to check that the action is symplectic. It's automatically symplectic. All right, so I promised 2 examples.
Yeah, before the second one, may I ask the question about the first one?
Sure.
So, so is it, so can this example be generalized to the case of action of compact Lie group on the tangent bundle of itself?
On a cotangent bundle. Yes, sure.
Yeah.
And in principle, here it depends a little bit. If we have enough time, we do it today. If we don't have enough time, that's the first thing we do next time in 2 weeks from now. Yes, absolutely. So this is a baby version of a calculation of an action of a compact, or actually any connected Lie group on its cotangent bundle. You're right.
Yeah, thank you.
Okay.
Excuse me, what was your remark? What was the statement? I didn't
The
get it.
remark is that the moment map condition implies the fact that the action is symplectic. Because you see, before the logic of the presentation was different. We were saying, let's study symplectic actions. And then certain symplectic actions are Hamiltonian actions. And if the action is Hamiltonian, then we can express it by the moment map condition. But now imagine that we have an example at hand where the moment map condition is verified. Right? You may still wonder whether the action that you started with was symplectic. And I claim that actually you don't need to check it again, because the moment map condition, it tells you that the action is Hamiltonian, and before that, it does tell you that the action was symplectic. So once you have a moment map condition, you no longer need to check that the action was symplectic to start with.
Great, thank you. And also, can you scroll back to the place where you used the Cartan-magic formula?
I use it all the time, but yeah.
The last time. Yeah. I mean next time.
This one?
Yeah.
Mm-hmm.
I don't know. Okay. So now it's clear. Thank you. I'm sorry.
Okay, thanks. So now, yeah, the second example, or maybe better say counterexample, it's also very easy. And now I have the two torus, S1 cross S1. And let me just see what notation that I want to use. So omega, so we have now two angles, and omega is d5h d theta. And I still want to act on the second S1 by rotations. So the fundamental vector field is just exactly the same as before. I again compute iota of xm omega. Well, I'm getting minus d phi. And well, here it's easy to notice that its cohomology class inside H1 is simply non-zero. So, right, so H1 is two-dimensional, one dimension for each of the circles, and d phi is a closed form, but it's not an exact form. So there is no univalued function which differential is equal to d phi, right? So here there is no moment map. Even though we'll see whether we have time towards the end of the course. But there is an exotic moment map. Perhaps we'll have time to discuss various kinds of exotic moment maps. So, you know, the moment map theory is so successful that people tried to extend the definition. Right now, we're looking at the standard definitions, but people invented many non-standard definitions which would have some or maybe all of the good properties of moment maps. So maybe later on we'll look into it, but at the moment, this is a counterexample. So this two torus, it has a symplectic action, but it doesn't have a moment map. All right. So the next topic that I want to discuss is uniqueness. Of moment maps. And here it's a very simple statement. Let me formulate it as a proposition. So suppose that we have an action of G on M omega, we assume that M is connected. So M is connected. And we assume that mu and mu prime are two moment maps. So then the difference is a constant element of G star. Well, proof is elementary, one line. So we choose some x in G, and we take the differential of mu prime minus mu paired with x. By the moment map condition, this is equal to iota xm omega minus iota xm omega, and is equal to 0. So this means that mu prime minus mu x is a constant for all x in G. And then, of course, right, this means that this element of the dual space is just a constant. So the moment maps, if they exist, they simply differ by a constant, and it is often used. We're going to see. So a somewhat more interesting example of existence. Well, I would love to present you a proposition saying that moment maps always exist, but I just showed you a counterexample, right? So it's not going to work. Of course, we know that moment maps exist if H1 is equal to 0. But let me show you one proposition, which is perhaps, I'm not sure whether this will be a bit surprising or maybe not. Suppose that G is semi-simple. If you know what it is, that's great. But if you don't know what it is, let's think of G equal to SUN out of our zoo of examples. So then the moment map exists. So you see H1 or not H1. So this is necessarily the case. Let's see why. So let's take an element in G, which is of the form of a Lie bracket or matrix commutator, right? Our Lie brackets are matrix commutators of two other elements, Y and Z. And we are computing iota of xn applied to omega. Well, we know that, right, this is the same as iota of ym zm, the bracket, Lie bracket of fundamental vector fields applied to omega. And now I want to use again the Cartan magic or Cartan calculus. I think we haven't used this identity yet, and I invite you to check it in simple examples if you don't know it. So this is the same as a commutator of the Lie derivative of xm and the of ym and the contraction with zm acting on omega? Well, this is equal to, right, iota ZM omega minus CM LYM omega. And the second term is 0, right? Because we are speaking of symplectic actions. So action is symplectic. So this is 0. Okay. So now this is L of YM and minus sign, and here D of sorry, no, that's not what I want to do. My apologies. Here I'm using the Cartan magic. Cartan magic, because I was about to use the moment map condition, but I don't know whether the moment map exists, right? So d iota ym plus iota ym d iota zm omega. But the second term is again equal to 0. Remember that iota zm omega, they should all be closed if the action is symplectic. So in fact, this is not there. And we get d of iota ym iota zm omega. And this is exact. Okay. So in fact, what we have shown up to now, that if X is a Lie bracket of two Lie algebra elements, say Y and Z, then iota xm omega is actually exact, right? If the action is symplectic, then this thing is exact. Now,
could you please repeat why the term iota d iota vanishes?
Iota d iota vanishes. Okay, yeah, let's look at it. So let's take this term. So there was iota ym d iota zm omega, right? Now recall that before that, today, we saw that this guy is equal to LZM omega.
Yes, thanks.
Okay. Right. So now what happens? So this form is exact whenever X is a Lie bracket of two elements, or actually, of course, the same thing would go for linear combinations, right? But now, if G is semi-simple,
Oh, by the way, we call a Lie group semi-simple if its Lie algebra is semi-simple.
yeah, yes, that's right. So then in this case, people write it like this. And this, in practice, this means that for every X, there is a presentation in terms of Lie brackets. So actually, everything is a span of Lie brackets in a semi-simple Lie algebra. And that's why it works like that. So all those forms, iota xm omega, are exact. And this means the moment map for symplectic actions of compact Lie groups is always Hamiltonian. Oh, sorry, semi-simple compact Lie groups is always Hamiltonian. So you cannot invent an action which would not be Hamiltonian. Note that we gave an example with S1 action. S1 is not semi-simple, and so that's why it worked. So again, I in case you don't know the Lie theory well enough, I invite you to check it for G, the Lie algebra of SUN, or if you want an easier life, for SU2. So these are basic examples with which we work, and there it would be great if you could check that indeed it works, that every X is represented as a linear combination of Lie brackets. So under this condition, the moment map always exists. All right. So now,
excuse me. So for one-dimensional Lie algebras, this proof doesn't apply.
No, this. But for the one-dimensional Lie algebra, right? We just gave a counterexample. So here it is, right? That's a counterexample to existence of moment maps. So iota x omega is simply belongs to a non-trivial cohomology class in H1. So it's not a Hamiltonian action. It's a symplectic action, which is not Hamiltonian. But if your Lie group turns out to be semi-simple, then it's not possible that such a thing happens, and then the moment map will necessarily exist. So that's a relatively convenient and strong property. So now I think that's probably the last definition for today. So so we have G acting on M omega. There is a moment map. And we say that this is a Hamiltonian G space. And well, now comes the condition which was requested already for quite some time. So that's the equivariance. Equivariance of the moment map. So you act on M by your G action, and you act on G star by the coadjoint action, and these two actions agree. So in other words, we say that so the moment map is G equivariant. All right, so this is an extra feature, and now we'll prove a relatively strong result, which is an easy result. So let's say proposition. Suppose that G is compact and connected, and suppose that there is a moment map. Then there is also an equivariant moment. So basically, in the case of actions of compact, symplectic actions of compact Lie groups, essentially there is no difference, because you can always find, if your moment map happen to be non-equivariant, you can always find an equivariant one. This is not always true if you step outside the realm of compact groups. In particular, there is a couple of problems in the next problem set, in the problem set 6, where in very simple situation, you first discover a situation when there is no equivariant moment map. There is a moment map, but it's not equivariant, and this cannot be helped. And then there is a way out. You essentially have to change the group checks, and then all of a sudden your moment map, the same moment map essentially acquires the equivariance property. So it becomes much more complicated once you consider the general case, and more interesting, one should say. But for us, I think let's start with easy things. So here is a proof, and to simplify our life, I do it for G equal to S1, but you can also do it for any G compact. And the idea is as follows. So let's choose, let's say, theta in S1. So let me consider a new function on M. Let me call it mu, or maybe let's simplify notation. So let me call it mu theta of M, which will be just mu computed at the point rotated by theta. So I use my S1 action, so I rotate my point, and that's so I build a new function. So I claim that this is also the moment map. So how do we check it? So so let's take d of mu theta paired with some element x. Well, what is it? So this is d of mu of m theta, right? X. And let me rewrite it several times. So I'm just using now another notation. So let me denote by g theta this rotation by theta, right. So this function of a rotated argument, that's the same as a pullback by g theta of the function, right? We usually kind of using pullback when we apply it to differential forms, but I can also use this notation for functions. Now, you know, pullbacks commute with a de Rham differential. Right. And mu was a moment map, so this was an assumption in the proposition. So this means that now I can use the moment map equation. Right. Now, in the case of the S1 action, both the vector field XM and omega, they are both G invariant. So you see, that's why I'm doing the proof in the case of S1, because it's an abelian Lie group. If the group were non-abelian, then the vector field would not be necessarily G invariant, and one would need to figure out what to do about it. So I challenge you to check what happens for non-abelian groups, right? So this this next step wouldn't work, but now it works very well. So it is minus iota xm omega, because everything is G invariant, and this is equal to, sorry, and that's what I want, right? So this proves the claim that m theta is a moment map. All right. Now the moment map condition is linear. So if I average, right, and that's the second time that we are using the average. So we define mu bar of m, which is 1 over 2 pi integral over S1 mu theta of m d theta. So obviously this is also a moment map. So this is just because the moment map condition is linear. And again, easy to check. It is now S1 invariant. And if you go back to the statement, what does it mean for the moment map to be equivariant, right? That's the equivariance condition. And adjoint star G is equal to 1 for abelian groups. So this means that for abelian groups, this equivariance condition is simply the invariance condition. So this proof can be easily adapted for any compact group, and for those who are interested, I invite you to do it. But basically, all the main steps are there, with the exception of this step here, right? Here you need to do something with this G going through XM. So XM would actually change when you apply this operation. But for the circle or for any abelian group, for any torus, this is just a good proof. So maybe now one more remark. So back to uniqueness.
I'm sorry, may I make a guess?
Yes, sure.
About your statement? Is it true that there will be in this place underlined with green that this will be a co-adjoint action of group on XM, and then it will seem as a problem, but when we integrate this will be cancelled?
Let's say, yeah, you're right, of course, or almost right. So you see, so here in the true condition, in the general condition, you have the coadjoint action. So we need to do something, right? This coadjoint action needs to disappear in averaging. And here, when you go with your group element G through XM, there will be adjoint action. So X is an element of a Lie algebra, so G can act on it by the adjoint action, and that's what's going to happen. So actually, you will have an action or adjoint action on X, and this would translate into the coadjoint action on mu. And of course, in this formula that I wrote here, you also need to add a coadjoint action. So you need to slightly to add the adjoint and coadjoint actions, which would compensate each other, and the argument would still hold true.
Do you mean that we need to add action of theta not only in the argument of mu,
Yes.
but also on mu? So
yes, exactly.
the conjugation. Okay.
So we need to basically, right? We want to average our mu. So we need to put the coadjoint action to the, like, we should take this equivariance condition, and we should move adjoint star to the other side, right? We desire that adjoint G minus 1 star mu of G dot M be equal to mu of M. That's what we want. So then this left-hand side, we should prove that the left-hand side is also a moment map, and then average using the Haar measure on our group. So that's, maybe let me write general formula. But here, perhaps I never know. Maybe I'm using the language that some participants don't know. So it would be something like that. So that's a general formula for the equivariant moment map.
Thank you.
Okay, okay. So wait. So now there was one more thing that I wanted to tell you today. Yes. Right. So here is one more remark. So back to the uniqueness property. Now you may ask, what is the uniqueness property for equivariant moment maps, right? Suppose that we have G acting on M omega, and we have two moment maps, and they're both equivariant, right? We already know that the difference between mu prime and mu is a constant, right? Now the equivariance property says that mu prime minus mu computed on the shifted point is equal to adjoint G star of mu prime minus mu computed at M. But now, since it's a constant, right? So this is C, and this is also C. So this means that this C is a constant in G star, which is fixed by the coadjoint action. And now there are two cases. So the first case, G is abelian, and in this case, the coadjoint action is trivial, and in this case, G star G is simply G star. So when you deal with moment maps for abelian groups, you can add any constant you like. It's going to be still a legitimate moment map. And again, back to the situation when G is semi-simple. So then it turns out that G star G, and this is essentially the same property that we were discussing before. That's a dual property. That one is simply equal to 0. So again, maybe check for G equal to SU2. So this means that the equivariant moment map is unique. So in the semi-simple case, the moment maps always exist, and an equivariant moment map is just unique. There is only one for a given symplectic action of a compact semi-simple Lie group, which is a nice property. So then essentially in many cases, there is no question which moment map to choose. Now for abelian groups, That's an open question. You need to figure out whether your moment map exists. Maybe it exists, maybe it does not exist. There is always an equivariant moment map, but typically there are many of them. So you have a choice. And sometimes it's a problem, but sometimes it's actually convenient that you have a choice. So there is this dichotomy. For the abelian case, in some way there is more fun, but for the semi-simple case, this is very, very rigid. I think that's a good point to stop for today. So as promised, in 2 weeks from now, we start with an example of a cotangent bundle, which is one of the basic examples. We're also going to talk about other examples, and hopefully next time we prove we'll see, hopefully we prove our first big theorem, the reduction theorem, which is the easiest of the 3. And I wish you good luck with the test, those of you who participate in the test in a week from now. Well, I don't know whether you have questions.
Yes, I have.
Yeah.
Yeah. So you have presented to us the kind of the only abstraction to Hamiltonian action. I'm sorry. Yeah. So if I have Hamiltonian action, then there is the only abstraction to an existence of a moment map, right?
Wait. But we discussed that if the action is Hamiltonian, then there is a moment map, right? I kind of first tried to cheat, but then you or someone else caught me, and we had this discussion on this page. So actually, the action being Hamiltonian and the action having a moment map, that's the same.
No, I mean your remark. Where is your course? Yeah, I mean the remark. Well, the first one on this page. So if the I mean not Hamiltonian action. So if I have action, then these this class is the only kind of is the only abstraction to
maybe just you're right, but maybe just to make it more precise, right? There is a class for each x.
Yeah. You're right. Yeah, but my question is: so is there any some kind of abstractions to have an action?
Oh, just abstraction. Suppose you have a manifold, and whether it has a Hamiltonian action.
Yeah.
Or therefore on that, yes, people certainly did study such things, but on that I would need to. I don't remember by heart. Sure, I think yes. There's certainly, let's say, depending on. I mean, there are more and more restrictive abstractions if you ask for an action of a bigger and bigger group. Maybe just to give you a feeling, of course, you can ask for abstractions for an S1 action, but then if your manifold is sufficiently large, it doesn't mean you have it, but it will be more complicated. Try to find those abstractions, but in principle, I think it's studied. There are some answers. But maybe just to give you another extreme example, suppose you have a symplectic manifold of dimension 2n, and you want an effective action. Effective means that everything works more or less non-trivially of a torus of half of the dimension. So then actually such manifolds, they are all classified, which means you more or less.
This is just quasi-toric manifolds. Yeah, so
yeah, or toric. Let's say toric. If you write, I mean, toric manifolds, you simply in some way have a list, right? They're classified by combinatorial objects, by those polytopes. So this means that there would be many symplectic manifolds which would not admit such an action. But I think there are answers, more interesting answers to your question, but I would need to look it up. I don't remember by heart.
Yeah, I mean, so I think basically it is not so easy to, so given a manifold, it is not so easy to understand whenever it is coming from kind of some polytope or.
Yeah, well, that's that as well. But of course, there maybe but there you can also probably figure out, right? Or I mean, figure out there are many properties of toric manifolds which are kind of special. Maybe.
Yeah, of course. So you can look on second homology.
Yeah, right. The homology ring. So there maybe you have chances, but certainly people are interested in whether, say, how to distinguish those symplectic manifolds which allow for symplectic S1 actions. Sure, that's a very valid question, and as I say, I would probably need to check what are the standard. I think there are some standard answers, but no, of course, it's difficult to imagine a complete answer, a complete like kind of criterion which would verifiable criterion which would allow you to address this question. But certainly there are some answers. I'll try to check and remind me if I forget to report on that.
I think so. So could you please show me the place where you presented example on torus?
Sure. Here it is.
Yeah. So this is example when we have Hamiltonian action but do not have. I'm sorry. So we have
A symplectic action.
A symplectic action, but it is not Hamiltonian, right?
Mm-hmm. That's right. That's right. Exactly.
Yeah, but is there any examples when we don't even have
an
action?
Probably, yeah. As I say, yes. I think yes.
Yeah, great. So, yeah. I mean, maybe you have kind of example in mind right now. Yeah. So if it would be really great if you can.
Sure. Yeah. I'll look it up. Sure, but I think yes. I'm let's say I'm more or less confident that yes, you can build examples of symplectic manifolds which wouldn't have any S1 action. Yeah. But I would any symplectic S1 action. But you know, of course, maybe I'm lying, but I'll try to get back to you with more definite statements.
Yeah, I mean, is it true that if manifold, if you have symplectic manifold and it has symplectic action, then it has symplectic S1 action, or it is not true?
Wait, symplectic action of what?
So suppose of some Lie group, for example. So
but then yes, sure, yeah, of course, because any subgroup, right? If you have a symplectic action of a group, then
I can take its maximal torus.
Or any S1 subgroup, right? And typically, of course, if your Lie group is compact, right, it would have
you're
S1
right.
subgroups.
Yeah.
So that's certainly
basically the kind of finding S1 action is kind of first attempt to.
Yes, that's the let's say there we would expect that this is the least restrictive.
Yeah. So if it does not have S1 symplectic action, then
no, it doesn't have any compact Lie group actions at all. Yes, that's true.
Yeah, thank you. Yeah.
Okay. Any more questions? Yeah, that was a good one. How is it? The usual way of saying that the question is complicated for the speaker is to say that this is a good question, right? That basically that's a synonym of saying that the speaker has no answer, at least for now. So that was a very good question. All right, so any more questions?
I do have a simple one about the commutation of D and A omega. You said that what were
Yeah.
the conditions and what was it for? I couldn't remember.
So so D and A omega, right? This condition, it happens when omega is S1 invariant. And if this condition is verified, then linear algebra tells us that we can find a normal form where A omega and D will be block diagonal with 2 by 2 blocks, just like here on this slide. So I claim that this is just a linear algebra, whatever, story. So you have two skew symmetric matrices, they commute. Then you can, I think by an orthogonal transformation, you can find a basis which would bring them both to this normal form at the same time. So that was the statement.
But what does it mean the thing in the red square that we use some G orthogonal basis? I mean, this fact doesn't depend on basis.
No, but let's say, yeah, sure. This statement does not depend on the basis, but the fact that those D and A are expressed by skew-symmetric matrices, it does depend on the basis. So we chose an orthonormal basis for G bar, and then in that basis, our operators, they are represented by skew-symmetric matrices. Because otherwise, if not, then the condition will be more complicated. Then, right, if G bar is Euclidean scalar product, but we chose a basis which is not orthogonal, right? Then you would have still some symmetric matrix representing G bar, and that matrix, it will enter. You can check how it works. It will enter the conditions on A and D. But I prefer to work thinking that my Euclidean scalar product is simply whatever, x1 square plus x2 square plus x3 square and so on. So I chose such a basis that everything looks standard as in high school. So then A omega and D, they are represented by skew-symmetric operators. So simply transpose is equal to minus the operator. So this,
okay, thank you.
So I think this does depend on a good choice of a basis. All right, more questions? Easy or interesting? Okay, people, thanks a lot. So then see you in 2 weeks from now. And again, for those who take part, good luck with the test next week.
Okay, thanks, Anton. Thanks a lot.
Okay.
Thank you.
Thank you, everybody. Bye-bye.